few folks, but no, that's all good. We're talking about the equilibrium communities this afternoon, and I'm just going to get moving right along. I guess I'm a few minutes late here, so I just want to stay right on track here with everything. What I mentioned this morning regarding equilibrium communities, well, after getting that launched and most of the units pretty much being constructed and almost to completion, we had figured we're going to be taking this to the next step. And the next step will be talking about how do you integrate that into communities, coming up with housing design and energy efficiency and healthy and housing. The idea is to say, well, you know, the communities themselves have to be well designed as well. Of course, to look at reducing costs and infrastructure, but to make it still more viable regarding how it's connected to transportation, accessibility, walkability, connectivity, and also making it peaceful, tranquil, and very nice for everyone, especially looking at adding on green spaces and so on. So with this, CMHC basically the way we looked at it is we'll be talking about the Equilibrium Communities Initiative, a jointly funded and equal partnership between CMHC and also Natural Resources Canada's CanMet Energy Research and Development Centre. Basically brings together also the intellectual and financial resources of both organizations for this. Our overall goal is to speed up the implementation of sustainable approaches to the neighborhood design in Canada. So we're doing this by funding and supporting selected development projects which aim to improve operational performance of their project by designing and developing sustainable communities. It's really a matter of thinking from a broader perspective that integrates design, decisions, and housing and land use mix with those about transportation, energy use, and water use. Another goal of our initiative is to measure and share what works with interested audience so that they can learn from the successes and lessons of these demonstration projects. There we go. So the Equilibrium Communities Initiative is jointly managed by and funded by CMHC's and NRCan's CanMet Energy Technology Centre. So it's under the Government of Canada's Eco Action umbrella. It'll run until the end of 2012, and it builds on the initiatives of CMHC and NRCan's energy efficiency, community planning, and water efficiency. So it builds on CMHC's Equilibrium Housing Demonstration Initiative, which is drawn on CanMet Energy's expertise. So in locations across Canada, the demonstration homes combine a source of energy-efficient techniques and technologies with renewable energy technologies to reduce their environmental impact. So the new initiative, with equal partnership from both organizations, is providing $4.2 million for technical activities and showcasing the performance of the selected development projects. The amount of the support which for each of these projects has been determined by the budgets proposed by each selected project proponents and also by the scope and effectiveness of the activities. Just to keep on track here, I'm just going to move up in this one. As far as the resources are concerned, roughly up to about $550,000 was made available for each of the project along with technical and showcasing assistance. So the funds for the activities aimed at design modifications that improve the project's environmental performance, including research as well as incremental costs for the resulting in design modifications. The funds are also used for monitoring, commissioning, and showcasing the performance of the development project. The initiative emphasizes innovation in planning and design and supports improvement in environmental performance. The initiative does not provide capital funding for the construction materials or equipment. So the initiative has identified 6 themes as common integrated framework for selected projects and measuring their performance. They address socio-cultural and economic themes, but focus primarily on environmental ones. More specifically, they focus on specifics that are most directly affected by urban form and which are mostly rarely measured. So first of all, we look at the energy efficiency, and the goal is to balance energy supply and the use and minimize greenhouse gas emissions. For example, the energy consumption in the project's building and its use of renewable energy and waste resources, or waste energy sources. This does not necessarily mean that all the buildings of the projects are expected to be net zero energy buildings, but significant improvements in building performance are expected in the projects. Another one is the land use and housing. By this we mean a compact community with a balanced mix of activities, housing choices, and commercial, institutional, recreational, and industrial land uses. Examples for this theme are used in land use mix, access to daily destinations such as stores, schools, parks, and jobs, as well as housing affordability. The next one is the transportation, which is about opportunities for energy efficient and healthy alternatives to personal vehicle use. In addition to the land use indicators described earlier, some of the indicators include the project's transit supportive destiny, transit proximity and quality, and pedestrian route and connectivity and safety. The other one is water, wastewater, and stormwater. And this is efficient use and disposal of water and minimal negative impacts on watersheds. So project teams were asked to describe the project's management, stormwater, and reduction of potable water use. And then we're into the natural environment, meaning a community that protects, enhances, and restores the natural environment. This includes habitat protection and creation, watershed protection, tree canopy coverage, and food production. And then the final one is financial viability. This means the marketable community that is economically viable over the long term. It includes the project's innovative financing and marketability and the long-term operational viability, amongst other criteria. The initiative was designed to explore options that are not viable at the smaller scale, to explore how working at the neighborhood scales with multiple buildings and land uses offers opportunity to integrate the systems such as energy and water systems. For example, the scale enhances the opportunity to capitalize on renewable and waste energy for use in community energy systems. The proximity of daily destinations and pedestrian family site design features make transportation alternatives viable, such as walking, cycling, and also public transit. One of the projects that we have, I'll just kind of quickly go through some of these, is Station Point. This is the developers, Communitatis group out of Edmonton. This is basically a transit-oriented development to be the first redevelopment in the Fort Road Renewal Project initiated again by the City of Edmonton on former industrial lands northwest of downtown. The project is planned to include 220 affordable and market homes in the form of townhomes, mid and high-rise apartments. The mixed use is expected to include over 1,400 square meters of commercial and retail uses and a daycare and also community facilities. So they're still in the planning stage. I had visited the site last year, and most of the stuff is the infrastructure is built around. The land is ready to go, it appears. One of the things that they have actually changed a little bit is more focus on instead of so much geothermal, they're focusing a little bit more on strategies for passive solar energy. So the site is located within walking distance of a light rail transit station and bus terminal, within walking distance of the key destinations such as stores and civic amenities. So the project targets a 75% reduction in building energy use, as I mentioned, through the passive house design features in the buildings. The initiative support is also being used for investigating options for treating 100% of the wastewater on site and will be reused for toilet flushing and irrigation. So I don't think they're going to, I don't know, they might be using it for watering lawns. Is Trevor here? I'd never realized here that maybe I guess we shouldn't be watering our grass and leaving it yellow, but you could use that water for that. So the project aims to divert 100% of the storm water from the municipal sewer through a combination of on-site infiltration and capture for treatment use on-site. The next one is the ampersand. It's the area in the green L shape at the lower right-hand side. Is the proposed development. On the upper right part of the L phase is the other section is phase 1. But you can see the adjacent retail and commercial uses in the other section. And it's located in Ottawa's Chapman Mills Town Centre area, South Nepean. Ampersand is planned to be a mixed-use neighborhood for over 1,000 homes, from stacked townhouses to mid-rise apartments. The homes are to be integrated with over 25,000 square meters of commercial space, civic uses, and also public open spaces. The next one is Regent Park Revitalization Project in Toronto, and we'll be hearing from Philip on that one coming right after me. Just a couple quick notes on that. It's a detailed part of the drawing phase 1 of the overall redevelopment. The remaining blocks are to be developed over several years, transforming Canada's oldest and largest social housing community into mixed income community for about 5,100 households. So I'm hoping that's still correct. Maybe more. Yeah, so I won't steal your thunder on that one because I'm actually a couple minutes over. So, and the other one is Taistanis near Tofino, BC. This is the only one that we have actually that is on First Nations. So you can see the planned housing in the center of the site plan. I don't know if you can see that from back there. Whoops, sorry. Where's my little down there? So the green areas represent vegetation, primarily consisting of preserved areas, along with some of the areas actually to be replanted. First Nations is developing a new community of about 84 hectares of land transferring from the Pacific Rim National Park Reserve. Consistent with the TFN concept, I have a hard time pronouncing this. Kanish Sawak is all in one here. Hishak Nish Sawak. I have to practice that. A commitment was made to explore and apply practical, sustainable community development principles. So the new community is to include 171 single detached units, 34 units of duplexes, and 12-unit elders complex. The road network on the other site servicing are complete, and some of the other homes are also under construction. The idea here with Taistanis as well, though, is that they're going to be building this with a geothermal system. And it's already mostly put into place. They're using the slinky system that goes just underground, and they plan on using this geothermal system to actually heat all of these units. I also have a publication that I have set up on the table there, and it talks a little bit more about the measurement performance and the themes and the indicators. So we have I think it's about 18. Yeah, we have sort of 18 different categories, which were used by the teams when they submitted their applications for this competition. And I like to use that as a sort of a benchmark, or sort of setting the bar, that if anyone's looking at doing subdivisions or redevelopments and so on, they can use this as sort of a guiding principle as to what they can consider using when they're designing their subdivisions. I think it's actually, that's a good piece on that. However, a lot of this information is actually available again online on CMHC's website. And if you go to sustainability, now this one here is Equilibrium Communities, and it'll tell you a lot about all these different projects. They do have profiles on it. And then we're learning as we're going. So this is sort of at the beginning stages. And I'll let Philip actually come up, and he could start his presentation. In the meantime, I know I rattled through this fairly quickly. I just didn't want to go over too much. Any questions so far on this? Yes.
Are you still accepting applications, or is there an RFP for new projects?
Unfortunately not. It's closed. It's done. The money's been committed, and now we're just hoping for the outcome. So it was the one-shot thing, just like the Equilibrium housing demonstrations. So, thank you. Yes?
Question. Just as a percentage, how much energy is saved by this type of planning versus maybe the traditional stuff? Mr. Guess.
Well, it's hard to describe here because, for example, if you just incorporate, just say, for instance, the concept of using a fuse grid. In that area, you could actually reduce the size of your lots, not to say that you want to be living really super tight to each other, but you could reduce the certain size of lots because you could also, and the street sizes, and also walkways. Because you might want to look at reducing the speed and the traffic in some of these residential areas because there's no need to have super wide streets. Of course, you got to keep in mind about fire safety. And most reasons why a lot of these subdivisions have these big streets and so on is only because of fire truck sizes, to accommodate the size of the fire trucks. But overall, it's still in such a way, if you incorporate some of these principles, that you can actually get more yield out of it. The developers is totally happy. It includes connectivity, walkability, green spaces, and actually less money that goes into the ground. As far as percentage, how much you save on that, you know what, I don't quite remember what the percentage, it's a little bit better. I mean, obviously there's profitability also in incorporating that concept. I'm not sure, maybe, I'm hoping that maybe Philip could eventually answer that type of a question further down the road, so I don't have really all the answers. Anything else? Okay. Well, I think without further ado, is someone supposed to introduce Philip? Well, I don't have the bio here.
But I don't either, and I don't know anything about it because I'm not already in printed literature, so maybe you could introduce me.
Great. Well, I have the honor of being able to get Philip Young to come up here. I've got him in from Toronto, and he's going to be talking about the project, and I know you're going to be blown away by all this, all the things that they're doing there over time. So. Welcome.
Thank you, Ken, for the introduction. Actually, I got a call from him, I bet just right after Christmas. And then he told me that, will I be interested to come to this part of the country? I said, where exactly is Bruce Jaw? And then I Googled the map, and of course, it's not that far from Regina Airport, and it's a straight highway. So I kind of boldly, and also not kicking and screaming, but it is my pleasure to be here, that be able to share the story. It may not be the great story, but in fact it is a true story that we've been struggling in Toronto for an old neighborhood that was built 50, 60 years ago. And it's not that much different from that wall house that Ken mentioned, that won the some kind of award, that been able to spend $80,000 to convert into a high efficiency single detached houses. And actually in Toronto there's a lot of these situations, whether it's detached houses, townhouses or apartment. Some of them are really started in the 60s, and of course there's a lot being built in the 70s with the three-level government providing some funding. So I'm here today, actually I'm very honored to be here, to be able to talk about this project, and not so much the project itself, but the way, the lesson that we learn, and also the opportunity that we can exchange this type of information that may not be readily available you know, in the industry and also in this part of the world. So I would just do, while the AV guy is helping me to pull up the slide, Toronto Community Housing is one of the, I would say, the biggest social housing provider in this country, and only second in the North America beside either New York or Chicago. So we are big in a sense that because of the different old housing that we inherited in the past, essentially City of Toronto only had a 8,000 social housing to start with about 20 years ago. But then near around year 2000, there's a a direction where the province, they want to download all these social housing responsibility to the municipalities. And therefore, we become suddenly from 8,000 to now we have over 58,000 housing units to be looked after. Let me adjust. I put too many PowerPoint here.
Not that one?
Yeah. Go back to the original. Yeah, close it. Okay. Yeah. Okay. Thank you. We found the slide. Okay. So this is the picture of the new building that was completed about 2 years ago, and this is the first 22-story senior building and also 8-story family building. They're all what we call low-income housing, and then I will show towards the end the whole picture of the phase 1 area that we completed. So just a little bit about the process of the revitalization and also the company itself. So as I mentioned earlier, we now have to manage and maintain over 58,600 units. They are home to 164 low and moderate income tenants. And the idea of revitalization is born out of necessity, because most of those buildings that was built 50 years ago, the infrastructure itself, the building envelope, the system are all aging. So it needs a lot of money to upkeep and also to maintain. And not only the infrastructure itself, but also there's associated social problem with the communities, and they also compound by the kind of design back in the 50s, where they employed the British Garden City concept, where there's no road that the police can get into the neighborhood itself. So it's all enclosed, a very neat but very enclosed neighborhood. So a little bit about our profile, that we not only provide 58,000 units, but also we have to deal with a lot of immigrants, a lot of senior people with special need, what we call vulnerable tenants. So those are the complexity we have to deal with, and not just the democratic, but also the aging process, and also different needs that we have to deal with right away. And we have more than 7 years to 8 years waiting list that they want to come into our housing. So it is a strategic component of what we call an asset investment strategy and portfolio renewal. Through public and private partnership, we redevelop, intensify, and also reconfigure the city neighborhood. So it is not just doing by ourselves, but we have to find private partner, builders or developer that have the expertise in dealing with this kind of redevelopment. And also we have to find a sound financial plan so that both partners can work together. So you can see some of the old black and white historical context of the early poor housing that was quite common in the late 40s and early 50s. So those are the what we call dilapidated houses that need complete rebuild. And you can see these are the housing that we are going to demolish and rebuild. In those days, in the 50s and 60s, they are already pretty solid housing, but over the years, it become fall apart because of the lack of funding. If you read the news, you can find in Globe and Mail and other newspaper that for a typical year, if we do nothing, we still have to add $100 million to the capital reserve in order to upkeep all our portfolio housing maintenance and replacement. Right now, we have a backlog of over 650 million. That was counted last year, so including 100 million this year. So we have a backlog of over 750 million. So you can imagine it is a tremendous challenge for us to be able to well manage and well maintain these buildings. So we're looking into innovative way to find resources, not only financially, but also human resources in the sense how we can generate new revenue, new income. So we have come up with two big ideas. One idea is what I'm going to talk about, the Regent Park revitalization process. The other idea is we cannot spend $1 billion to $2 billion like Regent Park to all our existing neighborhood. So it's totally impossible. So we have to look at from a different angle. How can we keep an old apartment building, like 60-story, 20-story high? We cannot afford to demolish those buildings, but we have to maintain it. So we are trying to look at a new working model that will allow us to save energy, save operating costs, and then generate enough new revenue to allow us to offset some of the capital replacement. So this is still in the making, and we will see whether that new working model will go hand in hand with this type of demolition, rebuild, and revitalize. One major aspect of any typical revitalization will have to involve local people and the communities. So engagement is a must. So about 6 to 8 years ago, before we really start any demolition, we talked to numerous people, tenants group, and also the city councilors. And throughout all these, what we call stakeholder consultation, and we collect a lot of information, a lot of input. But one of the challenges is that we cannot promise all the input we collected will become a reality that we can put into our plan. But all these activities behind, there's a trust between the landlord and the tenant and the communities. Otherwise, without this trust, the process will be derailed. There's a couple of key considerations. For example, the social, physical transformation of the community and the people involved, especially the people living in the existing building. The trust and capacity building for the resident, a long-term, honest, effective relationship with the community, and also addressing the barrier and creating opportunities. We use a lot of animators. This is a term that we come up with. In fact, they are people selected from the community. They live in the building, and we provide some kind of training, some kind of specific forum for them to understand our standpoint, our plan, and then they can go back to their communities to explain to their folks. Because we, living in the Regent Park, right now we have to deal with 7 languages, from English, French, Chinese, Vietnamese, Somalia. So there's a tremendous challenge in terms of cultural diversity. So that's why we need those animators to allow us to communicate more effectively to their needs. So what is revitalizations? As I mentioned, all these buildings are already built 50 years ago, and with the download from the province, there's no capital reserve to allow us to keep on repairing the structure and replacing the mechanical and electrical system. And in our overall portfolio, we are responsible for over 2,200 buildings all around the city of Toronto. And it comes in different size and scale, and also different value involved in those assets. So in a nutshell, out of these 2,200 buildings, there's about 61% what we call high-rise building. And it includes 36,000 apartments. And then another 23% what we call mixed high-rise and low-rise mixed building. And the third one represents about 800 low-rise townhouse and walk-up. That represents 14% of our overall portfolio. And they are mostly with families. And lastly, there's 2.5% what we call detached and semi-detached houses. And maybe you already read in the news that our company is trying to put over 700 all these scattered houses for sale to raise money to offset some of the capital backlog. It is not something we want to do, but if we cannot continue to have adequate funding, there's no way we can maintain the building and also look after the well-being of our tenants. This is a very clear layout of the existing Regent Park, where you see there's only like a surrounding road, and then you cannot get access into the middle part. So even the police, they said they cannot go into to have patrol into this area. Compared to the new design, you can see all very friendly and very strict and easy access to different parts of the new building. So one of the design challenges is that we have to create new roads. For example, in the phase 1, we already created 2 new roads that will not exist before. So in terms of the design ingredient, we have to create pedestrian-friendly connected street. We need to create more park and open space and have more community facility, such as we're going to put in an aquatic center, a huge swimming pool, and an open area like a huge garden in the middle. And we also add arts and cultural center. So there's a real need for upcoming young artists. They want to demonstrate the skills and the ability, and they want to get into this kind of entertainment business and performance spaces. And we also want to use diverse architectural design to make the whole new neighborhood look attractive. If you go to Europe, to Sweden, to other countries where they have similar revitalization, in one of their criteria, they want to select different architects and engineers so that they can provide a different taste and different outlook of the design. And in that sense, when the whole community rebuild, you can see the variety and that kind of mixed design, which make the place workable and beautiful. In terms of the new urbanism principle, such as compact walkable neighborhood, mixed-use urban form, highly connected street network, sufficient density, building design that emphasize human scale, range of housing to serve diverse population. At the left-hand side, you can see the old corner block. This is what we call Dundas Street, and this is the Parliament Street here. And you can see this is total facelift, where we demolished the old building and put in a brand new social housing that almost doubled the size of this old building. And we also create some retail space on the first floor. And there's a high-rise condo, kind of intermingle with the social housing. So it is not just an experiment, but it's happening since late 70s in Toronto, where we buy in the idea of mixed development. So we need to unlock commercial potential, and this is a fundamental difference from the old neighborhood where they only concentrate on providing residential accommodation. But now in the revitalization process, we recognize we must provide this kind of potential in order to provide employment for the people living in the area. So we have to provide a basic anchor and use the, those commercial entity to provide job opportunity to the new resident or to the surrounding area. So those are some statistics, the number of jobs we created through this community economic development process. So in the process of demolition, construction, we provided 56 construction trade jobs through our partner, Daniel. And also, Royal Bank provided 21 job opportunity, Rogers Communication, Tim Hortons, Fresh Company, which is a grocery store that provide 80 employees opportunity. So before the revitalization, there was no substantial employment. And now, through the new phase 1 and phase 2, we immediately injected this opportunity to our new neighborhood. So all these jobs were made possible by the introduction of this first neighborhood-specific Toronto Employment Service Office, who has led to the employment of 411 tenants since the introduction of the office to the community. So from that point onward, the Toronto Employment Service Office recognized this is a potential area, and they start to take proactive role in becoming engaged in other revitalization projects that are to come. So not only economically we provide employment opportunity, but also it is crucial to have a social development plan. So the social development plan is comprised of 4 major elements: the comprehensive background analysis, a social cohesion employment plan, and community service and facility plan. So we have to create a vision to advance the social agenda for the whole community. And our primary goal is to build a social inclusion and reduce poverty. Focus on community development and also emphasize on community services will facilitate economic development. So it's a kind of interrelated process. So this is the overall layout or block plan of the 6 phases of redevelopment. We just completed phase 1, the yellow part, and we're already starting construction work for phase 2. And you can see this part is the open space or open garden that connected the whole community. This is an aerial shot for the phase 1, which has been completed. The earlier photo showed this is the tallest building in phase 1, or actually in the whole new neighborhood. It's a 22-story building. I just put all the statistics so you can see. These are the 246 Sackville, 252 Sackville, and also 1 Oak. These 3 buildings are rental housing. And then we have the two market building. You can see the market building is right next to it. And then this is another building just completed. And you can see there's townhouses in the middle. So that consists of the phase one, which amount to about 1,000 unit, new unit being built in this phase. I'm going to spend a bit more time to talk about the district energy system, or what we call a community energy system, which is in the basement, the central plant that will drive heat and cooling to the whole 69 acres for the next 10-15 years development, which will provide heating, cooling, hot water system for over 50 buildings in this 69 acres of land. Up here is the cooling tower. So on the financing aspect, as I mentioned earlier, this is a public and private development. So we selected our building partner, as well as we want to create a value so that from the existing low density, we go to a moderate density concept. And that's how we come with the additional money to finance the social housing reconstruction. One of the concepts is that we are not going to ask the government to provide subsidy for us to rebuild all these old buildings, but through a slight densification, we've been able to team up with our private partner who will build condo, and then through the sale of those condo units and the profit we receive, we are going to split into 50-50. So the 50% will be, profit will be reinvest back to providing more of these new housing for the low-income group of people. The financial discipline is very important. We have to come with a business plan, look at the capital cost, look at the expenses, the ROI, the net present value. This is not one exercise that was done in the past. It had to be keep on updating until we are satisfied that this is a real business plan that will attract revenue and that can make the project ongoing. I would admit this is one of the biggest challenges among all this work, but we have no choice. We have to work closely with our partner. So who is investing in this revitalization process? We have a number of stakeholders involved. Our company, of course, the government of Ontario, the City of Toronto, the business community, the people of Toronto, and there's a lot more partner involved. So just a little bit of the financial number I highlighted here. Regent Park Reserve, to get it going, we want to make sure we have enough cash to cover the cash flow during this construction period. So we have to come with a long-term borrowing approach. And for the last couple of years, our company been able to achieve a Standard & Poor rating of AA-, which is a notch below the city rating. So this is actually quite good, and which allow us to issue 2 bonds, raising $450 million to pay for this construction work for phase 1 and phase 2. From the province and the federal government, they chip in $44 million into the affordable housing program for phase 1, and also pay for the soil remediation work for phase 2, which account for $5.5 million. And then the City of Toronto, they also have to put the skin on the table in the game. they have to put in 44 million for the public infrastructure. That represents only 60%. We still have to find another 40% to foot the bill. Now coming to the sustainability, the energy efficiency aspect. So how can we integrate that massive reconstruction with sustainability? So all the building that that you see here, we managed to achieve LEED certified gold standard. And so you can see on the very left-hand side, T6C corporate, we have a green plan, and we also aspire to achieve a CO2 reduction of 40% by the year of 2020, which is only 8 years from now. But we use the base years of 2003 to set the benchmark. So it is a very ambitious goal. So that's why when we have the opportunity to put up new building, we want to make sure we incorporate what Trevor had mentioned, the low flow toilet. We want to make sure the glazing, we achieve 4% wall area, and we use low emitting materials, low VOC material in the kitchen cabinet, insulated wall roof, stormwater for irrigations, and we want to make sure that it also ties with the transportation, because in Regent Park we have streetcar and we're very close to the subway system. So essentially we don't need to provide that much of parking, and we encourage tenants to use bicycle and walking to their workplace, and that's how we can reduce the parking area as well. So for the townhouses, very similar to what Trevor mentioned, and we managed to build all these houses 47% less than the modern national energy building code. So these are not small achievement, and also present a small bit of premium. And again, it is very important for us to note that the condo buyer or the townhouse buyer, they are not able to persuade that they have to pay more unless they can see the benefit or some tangible benefit out of this type of design. Okay, coming to the community energy system. So what is a community energy system? Maybe you're already aware of in Europe, in this country, we have the term called district energy system. Essentially, it's a central energy plant that either use steam, use boiler to create steam, and then supply the steam to different building, and then provide the space heating, and sometimes providing hot water supply through heat exchanger. So those are very old concepts. But what is unique in Regent Park is that we are not going to use steam, which is not a very energy efficient approach or media. So we decided to use a low hot water temperature and a slightly higher chill water temperature to provide heating and cooling and domestic hot water to all these new buildings. You'll see in the subsequent slide, this is a simple schematic showing how the new CS is going to work. So in the central plant, which is in the basement of that 22-story building, we have enough boilers. They are all gas-fired boiler. And later on, we'll add combined heat and power plant and other renewable energy supply to augment the production of heat. So essentially, this is a thermal heating and cooling plant. And then through the distribution piping, we go to each of the building, and in each of the building, we have a ETS. ETS stands for Energy Transfer Station. In the subsequent slide, I will show you some of the pictures. So it is very basic. A central plant, create a thermal grid, and then go up to different buildings. So one beauty of this system is that in the central plant, it is what we call technology proof. So in the future, if fuel cell is cheaper, then we can flow in a fuel cell and replace the boiler. Or we can put in CHP, we can put in geothermal sources here. The most essential and biggest investment is in the piping itself, because the piping is supposed to last 50 to 70 years. So once in the ground, it will be there for a long, long time. You don't have to repair and dig up. And then the ETS in the building is very easy to maintain. Essentially, it's just a simple heat exchanger to pick up the primary supply and then into the secondary supply to the building. So just to show some of the heating plant. For phase one, we managed to provide one condensing boiler, which is very small, about 1 megawatt. And then we put in two 4,900 kilowatt boiler. So when the whole central plant fully built, it can accommodate over 30 megawatt of heating to the whole neighborhood. For the cooling, in phase one, we put in 1.3 megawatt, 1 megawatt chiller, and then another 1,000 ton chiller. And we already put in 3 evaporative cooling tower on the roof. So all these equipment we put in are sufficient to last till phase 3, because we have to provide some kind of redundancy. So for the piping, you can see they are very like 250 millimeters diameters heating pipe, heavily insulated, and also chill piping as well. So you can see they are not that deep, and of course they have to be coordinated, especially in a urban setting where you already have a lot of power line, water main, sewers. Unless you are in a new subdivision, then you don't have to worry about all these. The energy transfer station essentially is a bunch of heat exchangers with meterings and gauges, pressure gauges. Although it doesn't look complicated, but we have to put in energy meters. This is the area that is very important, because the future consumer, when we build them, these are the revenue meters that we rely on. So the upkeep and recalibration every number of years are important to keep the business going. I mentioned earlier about using renewable energy, and both Cam and Trevor have mentioned a lot about renewable energy, and I'm very glad that a lot of the lessons learned also apply to Toronto as well. Although Toronto may not be as cold as this part of the world. Also, Trevor mentioned in Ontario, we are specifically blessed with the generous subsidy from the province to create that kind of green power. In Toronto, we are paying about 10–11 cents per kilowatt hour electricity. And the feed-in tariff, what we call feed contract, essentially this is targeting, encouraging people to put in solar photovoltaic on the roof. They are paying 80 cents or 82 cents for what we call micro feed, like below 10 kilowatt solar panel. They can get as high as 80 cents per kilowatt. And then it goes down to 72 cents or maybe 65 cents, depending on the overall capacity system you put in. So this is a very lucrative, incentive. But unfortunately, that only happened for less than 2 years. Now the Ontario Power Authority, having that deficit constraint, they are reconsidering, they are doing a major review. Obviously, the outcome would be a much lesser, incentive, and hopefully, it will not kill the industry, but likely it will really damage the good work that they have created in the first place. But nevertheless, we still have a lot of opportunity to put in solar thermal, which is providing hot water, preheated hot water, and also solar wall, which is those black, ugly metal cladding that also absorb the heat and then preheat and circulate the air into the building. So those are very viable options that we keep on considering and putting into our building. So one of the examples, we put in a small 5.94 system in our head office. So this is in a very tight roof space. As you can see, we have a cooling tower up here. And so we managed to squeeze in, I would say, around 22, 23 solar PV panel. And we did some measurement, and this is what CMXC provided best, is the grant money that allow us to continue doing monitoring and refine the design. We found out over July to February last year, the system in fact can produce 4% more energy than originally predicted, which is quite good. So we hope to continue to have this kind of information, and then obviously we will do a proper analysis, and then we'll inform CMXC as well as other stakeholders as well. So Morse Park is another 1,000 unit housing, old neighborhood, old housing in close proximity to Regent Park. So you can see the dotted line that we can connect it to Regent Park. Regent Park is right here. So once we have a district energy system, we can count on the expansion of the piping to provide heat to nearby building. So that's how the business development can grow. So some of the lesson learned and some of the challenges we are facing while doing this project. On the project vision and feasibility stage, it is most important to provide a concept and also with local champion. I was talking to your mayor, Helgo, and also the councillor, that I really encourage, and as the political figures, we have to rally this kind of political support to drive this type of sustainable energy going forward. Without their support and championship, I would say you will either have a project, but you will suffer a lot of delay. So this is one hard lesson we learned. Without that political influence, it's really, you just can spend a lot of money doing consultation work, but it goes nowhere. Secondly, we have to do business, what we call options appraisal. Look at the base case. If we put boiler and chiller on each of the 40 buildings, compared to putting a central system, in a 30 years, 50 years life cycle costing analysis, what is the NPV, what is the long-term benefit? So once you carry out this objective analysis, then you will be able to convince the chief executive to look into proper investment that will bring long-term benefit to the community. Again, we understand in reality, most of the builder and developer have a relatively short outlook, maybe 2 to 5 years, whereas for the city, we should have a longer outlook for the benefit of the community. So it's an issue of how we can marry, come to a middle ground, short-term horizon and long-term vision. Thirdly, selection of knowledgeable consultants. There's plenty of knowledgeable consultants around, but we have to find people that have real experience that can add to the success of the project. And in our case, we have to do a request for proposal and seek expert advice going through an open process. On the design and construction stage, project delivery and procurement options, we have to look at it very closely so that we will not miss any timeline. Selection of design consultants and builders, I talked about this already. Especially in project like this with a central energy system, you really have to not just bring in a central energy expert, but also the regular mechanical, electrical consultants. They may not fully conversant with how to do the interface. So if they are using a constant flow design, whereas on the central system, it's very much the efficiency depend on using variable speed design, then you really have to sit down and openly discuss how the secondary or the building science system design compatible with the central plant design. And that's the integrated design number 3, the point number 3 is all about. I talked about the inclusion of future renewable energy already. I won't be labor on it. Lastly, the commissioning and operation stage. Proper commission is always overlooked or underestimated. And without proper commissioning, a lot of the design intent will not be realized, and the efficiency will suffer as well. In our case, we hate to admit, but the best consultant also sometimes they overlook, they cannot forecast what would be the construction, the development progress. So we initially suffer from a low thermal load, and that causing we invested ahead of time. We put in too much boiler and chiller capacity, but the occupants, the people moving in, are much slower than we expected. So the plant efficiency will suffer, and also we need to bring the customer in so that they can understand how the system works. And most importantly, training of building operators to understand how the system works. So lesson learned, commissioning is important, design versus actual load. In a LEED certified building, we discover the best projected load may not tally up with the actual thermal load requirement. So why is it important? It is important in the sense that in your design for phase 2, phase 3, and phase 4, we have to inform ourselves what is the actual thermal load for that building. And that will lead to a much leaner design in the future and saving a lot of costs. And without this information, if we keep on looking for the, from the textbook design point of view, we may be wasting some capital. Equipment sizings, we talk about communication between building automation system and the central plant SCADA system. They have to be hand in hand. So right now we're doing a lot of these exercises to make sure that the local building information can be shared with the central system so that we are accurately sending right temperature to the secondary and tertiary building. This is a quick snapshot of the saving from the early days. A typical building, the old Regent Park, is costing that much of money to provide the water and electricity and gas. And for the new Regent Park, we are at least 30% lower than the existing building. So it is quite a market achievement so far. But of course, there's still room to make this even lower. But we will not be able to achieve net zero. It will be very expensive for us. There are some actual figures showing the heating, cooling comparison to the old building, which is the base case, and then the new building, Dundas Sackville, and the variance here. One thing we also find surprise is the electricity seems to consume more than the old building. I think maybe Trevor has some answer already when he talked about the ERV, the HRV. If they're running all the time, obviously they have to use quite a bit of electricity as well. But once we know where the electrical equipment or mechanical equipment driving the high consumption, then we can find a solution over time or quickly. This is another screenshot for the monitoring equipment we're using. We're trying to get real-time metering so that we will not waste any saving opportunity. When we receive the energy bill, it could be 3 months, 4 months after the event happened or the anomalies being discovered. So with a real-time monitoring capability, we can respond right away and able to manage those waste or saving opportunities. So the conclusion would be partnership. A project like this, even in a city like Moose Jaw, I think it is important to recognize we cannot do things alone. We need all kinds of partners. We have to align our vision and value together. If the value is not matching, it's better to don't force the partnership to come in. Green buildings, architectural excellence, urban design, financial discipline, all these are important. And as in the morning we talk about the real estate market, it has to be marketable. So if we aspire to do net zero, but if it is not marketable, we cannot sustain that momentum. It will become a hard act to follow. So we want to revitalize our old neighborhood, but at the same time we can attract a new condo owner to move into the neighborhood. Continue investment, put the skin in the game, and keep up the momentum going. So these are some interesting statistics. So who want to guess what is the first number here? What does that represent? Any good guess? Yeah, right. This is the sale price for the townhouse that you saw in the map. So, and then the second number, 411, is the job created, only in this phase one. And then the 40% is the energy efficiency we're able to achieve. And the last one is very difficult to guess. Remember early on, we created some retail space. And remember Tim Horton? These are the townhouses relative to the high-rise behind the picture. And this is the demolition of the old Regent Park. This is one of the new building. The 1,000 donuts per day we're able to sell. So we serve 2,000 customers per day. So this is the good news, right? So on that note, I will just pause and just to see if there's any question. Yes, sir.
You're doing a redevelopment of basically undermanaged previous developments from 50, 60 years ago. And how do we keep from making the same mistakes when we see the sprawl of single-family dwellings where in 50, 60 years we're probably going to be coming into the same thing? Do we have to have federal provincial laws in place to prevent this, or whose job is that to maintain? Because we are repeating history, basically.
This is a very good question. Actually, I also think about this question a lot. Well, at the highest level, we are all human. No matter how you are an expert, you cannot predict the future. I bet 50 years ago when the planner, designer, import the garden city concept, they always believe this is a great idea, and that has been successful in UK. But after 50 years, there's so many demographic changes, new immigrants moving into Toronto, and there's a lot of socio-economical situation that nobody can predict. So I hate to provide a perfect answer whether the revitalization will be a success, but at least in the short term it works, and we bring in partner, we bring in investment, we tested out the mixed development concept, and we look at it from a socio-economic and environmental angle, so that those are the best available measurement or matrix that we have right now. And we cannot really predict the future. But one of the things we can learn throughout this process is that as long as we have an open mind and we work closely with the planner, the councillor, and all those partners, and listen to them carefully. And is that Cam? You mentioned about the flexibility, the flex house. I think with that kind of flexibility built in, I think we can go a long way. No question?
I'm not going to stump you on anything. I'm just could you elaborate a little bit more on maybe describing the partnerships? Like who specifically? Is it private money? Is it other types of investors that kind of went in on this, or is it more with city?
Yeah, in our case, it's very site-specific or project-specific. I guess in different country, in different part of the country, you have to really feel your way through to see who are the partner available. In our case, we have two major partners. For the construction, for the condo building, through our open process, we selected Daniel as our building developer. We choose them because they have experience in the residential market. They know how to market a new unit. They had a really firm ground in the community. And of course, we have, just like your checklist, 5 pages of criteria. They have to understand this is a new neighborhood, and we have a sustainability agenda. They have to buy in. So all those things have to work out. From the financial point of view, since we've been able to borrow money at a much lower interest rate, around about 4% at the time, 4 to 5%, so we're able to raise the initial capital to at least manage the phase 1. Whereas now we're into phase 2 and phase 3, we may not be able to use this formula. We have to find another new investment. The private partner may have to come in with the money. On the central energy plant, it's a slightly different story. We also go through an open process. We selected one utility company stationed in BC, and then they become a 40% partner. Our company still hold 60% partnership in that joint venture deal. So they provided the management skills, the technical skills, and to market the energy supply to the condo owners. So, sorry, Councillor.
Just maybe comment on the social animators. I'm assuming that these aren't people who are sort of experts in social work and facilitation, but rather people that were sort of culturally specific to deal with different communities on language and culture and so on, or a mix of both?
Yeah, you're absolutely right. They don't need to be expert, and obviously they are not expert, but they are willing participant. They are motivated. They want to help the community where they belong. So we selected among our different tenants group, and then select people, and then we bring them in, provide training, provide a different working session, so that they can fully understood our plan and the process. So they will go back to the community, and then they will have their own focus group or a different session using their own language, so they feel more comfortable to share that kind of ideas, and then they bring the feedback and input back to us. So it's a very versatile, and I think it's some kind of social marketing as well. So we find it a very useful, powerful tool for us to engage people. So I'm not sure.
Yeah, it's something we're not very good at here. It's a good lesson for us to learn from.
It's a challenging process, I would say, but we don't have any choice, because either we don't listen, and then we make mistake, or we pay, the cost to go through that process slowly.
Thank you.
Yes, Trevor.
More technical, logistical question, but with that central space condition with the heating and cooling, do each of the individual units still have control over their conditioning?
Yes, they do have. Essentially, the essential plant only provide a primary supply temperature, so it depends on the individual suite how they regulate, how they need the heat or cooling. If they go on vacation, obviously they are going to only maintain a minimal temperature, and there's like the fan coil system in the suite able to achieve that.
So there's a constant supply from the central to each unit at all times that's available to pull?
Yeah, the primary supply is to the building. We have a primary and secondary exchanger in the basement. So the secondary heat exchanger will do the job to receive signal from the building in terms of demand and load, and then it will send back to the central plant. It will adjust the incoming and outgoing temperature from the heating and cooling.
So a related question is, so is each unit metered separately? Do they pay their consumption, or is it?
Good question. Well, when I was in UK and Europe, they usually have that kind of suite level individual energy meters installed, and so we originally also thought of putting those individual energy meters, but the condo market building, they decided not to use it. Simple reason being it involved an additional cost. And not only that, from my understanding with our UK partner, they also advise us, once we put in energy meters, every 5 to 10 years, you have to include a maintenance cost, because those energy meters, although most of them are from either Denmark or Sweden, they are expensive, but also they're accurate. But after 5 years, you have to recalibrate. So if there's no specific business case to support the individual suite metering, it's not a bad idea to do a bulk metering and then a portion based on the floor area, which is quite typical in Toronto. Having said that, we also, because of CMHC grant, we're able to do 2 buildings. We put in individual energy meter, simply because we want to understand the consumption profile or pattern of individual tenant, so that we can do education or conservation measures, and also the real-time information is very powerful. We can use that to stop waste and also troubleshoot right away. Again, it's a cost involved. So there's no clear answer, depending on your objective and outcome you want.
Any other questions? Well, thank you.
We're going to resume our conference. The next speaker is Brian Brunskill, who, as you can see, is going to talk about geothermal energy. He's an expert in that. Not only the idea of bringing energy up from warm aquifers, but also disposing of carbon dioxide by putting it back into the ground. So please welcome Brian.
Hi everyone, thanks for coming out. I'm going to talk about geothermal energy, a little different kind of geothermal than you probably have set up in your mind. I want to thank the South Central Enterprise region for inviting me to make this presentation. They've been really great supporters of this new kind of technology for Saskatchewan. My background is petroleum geology. I've worked in Saskatchewan since the mid-80s, I guess, mostly on petroleum exploration and development projects. And as a geologist, I've become familiar as best I can with some of the features deeper in our Earth than what we think of right at surface. And one of those realizations is the presence of a very deep aquifer that is full of hot water that hopefully we could utilize as a real geothermal source. I'll make the distinction right now. The notion of geothermal really brings to mind of what are actually ground source heat pumps that you might have in your backyard, so to speak, or in other commercial developments, which are fairly shallow. I'm going to talk about a more traditional, prior to heat pump technology development, the actual use of deep geothermal energy, where we go deeper in the earth and extract water that's already hot. This picture here is of a drilling rig at the University of Regina over the winter of 1979-80. And at that time there was a proposed development for a number of new buildings, and the geological department and the university administrators thought it would be a brilliant idea to do an evaluation for a deep geothermal test for these buildings as a science project, particularly as a science project because there were no real discussions about greenhouse gases or CO2 emissions, those kinds of things at that time. So this is on the south side of the campus. The drilling rig is located what now is in Innovation Place. So this well has since been abandoned, but it's under the parking lot in Innovation Place. So in 1979, 1980, the winter there, they drilled this hole to a depth of about 2,200 meters, or a little over around 7,000 feet, to access this aquifer, what we'll call the Deadwood Aquifer for simple terms. And they did all the tests necessary to find out the actual value of this resource and the nature of the rocks in this location. And all that work was done, and during the process the university decided they were going to postpone construction of these additional buildings. So the second well necessary was not drilled. You need two wells to develop one of these. You have a source well, which brings the hot water up, and a disposal well that returns the now cooled water back to the aquifer. So the project was never actually completed, but we learned everything we needed to know about the resource at Regina. And by inference, with our experience with the same aquifer has been evaluated, not for geothermal, but geologically at MJEAC Belle Plaine, and other more distant oil exploration wells in the area, that we have a very good idea of what the character of the geology is right under the city of Moose Jaw as well. So what is geothermal energy and where does it come from? The center of the earth is naturally hot, due mostly to radioactive decay. This heat is trying to escape all the time and rising to the surface. In places like Iceland, that heat is expressed very close to the surface, but in the middle of continents like Saskatchewan, it has a harder time getting through all the continental rocks, so we have to drill for it. We have to go a bit deeper into the earth to find water that's hot enough that is commercially viable. This just shows the relationship between the general relationship with the deeper you get, the hotter the rocks get. The rocks themselves is what holds the heat, and the water in an aquifer would be the carrier. That's actually how we get the heat out from the deeper rocks. This is block diagram Saskatchewan. There's Regina and Moose Jaw there, and Estevan down here, and the Missouri Coteau, various other features. If you look at that black line, that represents the exposure of the Precambrian shield. So everything north of L'Orange is exposed Precambrian basement rock, we call that. As we come, if you look at the side of the diagram now, as we come down the side here, as we go further and further south, what we're actually seeing is an ever thickening wedge of sedimentary rock. And it's in this beige band right at the bottom that's the Deadwood Aquifer. It's a very widespread sandstone aquifer throughout much of southern Saskatchewan. And it is that actual layer of rock that hosts the water. So beneath Moose Jaw, that aquifer is between 2,000 and 2,200 meters deep, a little over, around 7,000 feet, say. And whereas at Estevan, because it's deeper, right around the border, it's about 3,500 meters deep. And to express that general relationship between depth and temperature, at Moose Jaw it's about 65 degrees C, whereas at Estevan it's about 100 to 110 degrees C. And that's really just a function of it being deeper. We have to have some kind of a map with contours on it. I am a geologist after all. This shows this relationship. This is the temperature, the estimated temperature of what we think the rocks are at that Precambrian surface in these locations. So you'll see at Moose Jaw it's about 65 to 68 degrees C. Weyburn it's up to about 80, 90, about 80 degrees at Weyburn, and close to 100 to 105 degrees at Estevan. And again, it's the same pancake or layer of rocks throughout the southern part of the province. They just get deeper, which is really reflected by these contours. Right down at, this is the deepest part of the geological section in Saskatchewan, and therefore the hottest. Well, how do we get that heat out? We have the ground level and then the presence of this Deadwood Aquifer. It's again a very widespread aquifer. It's the water within the aquifer itself is not moving very much. It's fairly stagnant. So at surface we have two wellheads that are very close together at a convenient location to wherever the load is going to be. And from there are two wells that are directionally drilled, which means we can drill sideways for a while. And in this case, again, this is based on a model that was presented by the work done at the University of Regina. So we have the source well here, which draws water out of the aquifer to surface. It is transferred into a heat exchanger plant, where the heat is given up to the heat exchanger, and then it's immediately returned down the disposal well. It's important to, this is a closed loop system. We don't want any oxygen to get into this system. It's got a very high salt content, and it could be potentially corrosive, so we just keep it completely separate. There's no oxygen allowed into the system. So this now cooled water, as it travels down, passes through the rocks again. It's drawn back to the source well again, but as it comes back, it's reheated. So we have this loop going around and around, but the water is reheated because of this massive storage of rocks. On the heat exchanger side, we have a freshwater loop or a glycol loop that would satisfy the load, whatever that load happens to be, a commercial application or a number of houses in a subdivision or whatever the load happens to be. As this cool water goes back into the aquifer, it actually starts to cool the rocks down and creates what's called a thermal front as this water is circulated around and around. And that thermal front slowly moves towards the source well, and eventually it interacts with that, and the water temperature would start to decline at that point. Again, based on the modeling work done at the University of Regina, based on full capacity pumping, which is we'll get to some of those numbers in a moment, this thermal breakthrough would happen, if this thing was run 100% of the time, this thermal breakthrough would happen between 25 and 30 years. Now, this is a low temperature resource that's suitable for things like district heating that we've learned about just in the previous talk. So it actually isn't useful in the summertime. So if we look at it operating in capacity for the winter, and then at partial capacity on the shoulder seasons in spring and fall, and it's essentially turned off in the summertime. We've actually doubled the overall capacity, so we've gone up to 50 to 60 years that one of these things would last for a heating source. Now again, that's based on 1,000 meters separation. We can increase that with directional drilling up to 1,500 meters quite easily, or whatever the planned load might be. These things can be adjusted into the overall plan. As is brought forward, we don't want to oversize something necessarily. This is a picture of what something like a district heating project might look. You saw the underground buried pipes in the last presentation. In this case, this system has 2 source wells and 1 disposal well. The hot water is passed through the exchanger plant and returned to the earth as a closed system. And on the heating side, we have hot water that's distributed to the residential, commercial, and industrial application in this cartoon. It's much easier to push fluid down than it is to pump it up. So if the load was there, there's economies of scale by actually having 2 source wells and 1 disposal well. You essentially get double the heating capacity for only half more of the cost kind of thing. So again, these kind of things would follow into whatever the final application might be. Well, what do we have actually at Moose Jaw? Based on our investigation so far, the aquifer itself is about 2,000 meters deep. It's actually 245 meters thick, or 800 feet thick. If you can just imagine, this is a sandstone body 80 stories high, full of hot water. It's a massive amount. It's a massive amount of heat sink and the availability of hot water to actually move that heat around. We estimate the temperature to be about 154 degrees Fahrenheit. I'm going to bounce back and forth with Fahrenheit and Celsius as well. It seems the industry tends to use more traditional imperial measures, so I guess both are useful. The delta T is that tells us how many degrees Fahrenheit we're stripping out of the water. So in this case, the water would go into the exchanger at 154 degrees and come out at 70. So we've stripped out 84 degrees out of that stream of water running through the exchanger. Now we're producing this water at 660 gallons a minute, or about 2.5 cubic meters. This is quite a high volume. So you can imagine that volume of water with that delta T generates about 28 million BTU per hour. Well, that's just a big number. If we consider commercial baseload heat, and I'll come back to baseload in a second, but if we consider how much space can 28 million BTU provide, it's about 1.7 million square feet of commercial or industrial space. And that's based on a conversion of about 16 BTU per square foot. 1.7 million is a big number. To put that in perspective, that's about 18 CFL football fields. So 18 warehouses, each the size of a CFL football field. Or to put into context of housing, again under kind of optimal conditions, if we had 2,000 square foot houses, that could provide, again, base load heating for about 690 houses. So this is a significantly sized energy source. So it needs a large footprint. It needs a large load to make it viable. Now, base load refers to the amount of energy that is required more on average. Like, say, the average temperature in Saskatchewan in January is -15. Well, this system would be designed to provide all the heating necessary to -15. And then that, for colder days, that heat would be supplemented by natural gas. So this wouldn't work in isolation. There'd still be a gas. If it's a house, for example, there would still be a natural gas furnace working in conjunction with this. They would work together. To put the energy in a different perspective, it's equivalent to generating about 8,100 kilowatts, thermal kilowatts. Now, it takes electricity to pump all this water around. That's really all we're doing is circulating water. And an estimate of about 366 kilowatts would be required to pump all the water around. So if we take the kind of the relationship or the ratio between the thermal power generated and the power consumed, our COP, or coefficient of performance, is just illustrates that ratio, is about 22. That's a significant return on energy in versus energy out. We can estimate an economic value from this hot water. Our infrastructure costs, our development costs to drill the 2 wells and to create this energy hub, this heat exchanger plant, and all that infrastructure, essentially getting it to a point where you have a manifold where a building could plug in to receive the water, is about $5.8 million. Now that does not include the distribution system. We've already brought up the idea of a district heating system to actually take that hot water to the load. This does not consider those capital costs. The value of this, of course, is equivalent to the amount of natural gas we don't have to purchase. And the avoided cost in this first year is about $1 million. Now we based that value on, when we did this assessment, a couple of years old now, was the Sask Energy 5-year contract delivered price for natural gas was $7.50 per gigajoule. So we used that number and set our forecasts up from there. And this also relates to operating only 183 days per year, about half the year at capacity. The net present value on that cash flow stream is about $5.5 million, based on a 6% decline rate over 20 years, or a rate of return of just under 16%, and years to pay out 6 to 7 years. It was this element that really brought my attention to of deep geothermal energy. This is why I became fundamentally interested. Is that this water is already hot. There are no hydrocarbons. There's no hydrocarbons need to be combusted to generate this heat. This is an endowment that's available to us right now. We just have to pump it to surface. So by avoiding the equivalent amount of burning of natural gas saves us about 7,300 tons per year from this one system. Now we have to buy electricity from Sask Power, and they have CO2 emissions, so we back that out. It's equivalent to about 1,200 tons per year. So our net emission avoided from this entire system is about 6,100 tons per year. I put the next line in for general interest, I guess. There's no trading scheme in Saskatchewan right now for a CO2 credit or an emission credit. There is a scheme for final emitters in Alberta, and there is discussions in Saskatchewan for some kind of potential legislation down the road that may put a similar value on the avoided production of CO2. But for interest's sake, that 6,100 tons is equivalent to over $92,000 per year, if indeed there is ever a market. This is another reason that I'm drawn to geothermal in this case. If we express these 3 different pollutants in terms of tons per kilowatt year, we see from coal, which is our primary generation of electricity in Saskatchewan anyway, is about 7.5. The NOx and SOx, the nitrogen and sulfur compounds that are associated with combustion of hydrocarbons are there as well. Oil is better. We don't burn much oil for heating in Saskatchewan, except in some remote locations. Natural gas is our primary heater. But you'll see the significant change as we move from any of these hydrocarbon-based fuels right down to geothermal. Again, because there's no direct combustion involved. This is a little dated, but I suspect it hasn't changed too much. This is the per capita carbon dioxide emissions in Saskatchewan and each province. The Canadian average is about 23.1 tons per person in Canada, and Saskatchewan we're almost at 72. So I'm very eager to encourage all and any kind of alternative energy or new energy that can reduce this footprint. Some of the benefits, of course, this is available for a long term. Once this system is up and running, it's available for a generation or 2. It's environmentally friendly. There's no direct greenhouse gas emissions. It's both sustainable and reliable. Again, the size of that deep aquifer, its thickness, its mass, it's very reliable, very predictable. It doesn't matter what the climate's doing outside. This energy is available at the flick of a switch. You just have to turn the pump on. And of course, unlike hydrocarbons, it's not subject to significant price volatility. Once this capital cost has been invested, the energy itself is well, we don't know how it might be priced with the government and such. There might be some prices associated with it, but it's not going to be subject to the volatility that carbon markets are. Of course, it's non-transportable. You don't want to pump hot water around unnecessarily, so it really has to be constructed very close to where the load is to avoid that kind of development. Like many other non-carbon-based fuels, it requires significant upfront investment. And of course, the timing of the development schedule is important too. Because it's a $10 million or $8 million investment, for example, you want the load present for it when it actually comes on stream. So that might mean a rollout schedule where you have construction where everything built is geothermal ready for the first 5 years, and at the appropriate time the geothermal system is actually built to handle that load. It can be used for many things, really anything that requires heating. Our homes or apartments and new residential subdivisions, hospitals, multiplex facilities, swimming pools, and of course new industrial park development. On a commercial scale or an industrial scale, it could be used for preheating industrial boiler or process water or large volumes of ventilation air. And of course, you guys know all about tourism and geothermal in Moose Jaw. What's exciting about this, and kind of boring, is that this technology is not new. We have everything in Saskatchewan we need to fulfill this right now. We have abundant drilling experience with our petroleum industry, and mechanical engineers on surface can easily design systems to pump water around, so there's nothing new about this at all. It's been used in Europe for 50 years. Many other countries as well have been using this. I visited Holland last summer to a geothermal project that was actually being drilled at the time, and the subsurface geology is very similar to what's happening with what's around Regina and Moose Jaw. And it was like, again, they were just very familiar with it because it's a much more commonplace in Europe. So all these, there's no intellectual property rights, and materials, all the stuff we need is not quite a Canadian Tire, but not far from it.
Next week.
Just as an example, since the 1960s, France, of course, they have never been endowed with a lot of hydrocarbon-based fuels, so they've been reliant on other sources. They've been more interested in developing other sources. But since then, they've developed 61 district heating projects using deep geothermal, and provide the heating for about 200,000 residential units. And for France, it replaces the use of about 1.2 million barrels of oil equivalent and saves on the emission of about 600,000 tons of carbon dioxide. This is technology they embraced many years ago. So we're all looking for different ways to reduce our environmental footprint and develop and utilize new forms of energy as they're available. And I think utilizing deep geothermal has the potential to satisfy both these needs. Each system can provide an essential cash flow stream for a generation or two, one that is very reliable and very predictable. It's probably a very secure type of annuity vehicle. Of course, we don't have one of these operating like this in all of Canada. We came close at Regina, but that was never completed, of course. But a commercial scale project at Moose Jaw would be the first of this kind of activity in Canada. And this is another interesting perspective. It doesn't require any big utility to build it. A community can build it, a joint venture could build it, industry could build it. Again, all this technology and knowledge is available off the shelf. This can be built and financed and in any way that's suitable for a community to do itself. So this is actually a two-part talk. We've gone on with the support of the South Central Enterprise region to do a bit of a case study, a very high-level case study, which I'll get into next. But I'm going to stop right now with this in mind in a very general way and ask if you've got any questions at all about any of this. And we can pick that up again later at the end of the talk. Sure.
You said, of course, you have to build relatively locally for where you're going to use it. What would you say the perimeter would be from a well setup?
Well, once the wells are located, they can be in a parking lot. They take quite a large footprint to actually drill, like 2 or 3 acres for a drilling site.
Right.
But once the activity is done, there's just a wellhead sticking out of the ground, and it would have something not much more than require the space of a car.
No, I mean, what the service perimeter that you can service efficiently.
You mean the geographical area of a well? The smaller the better.
Right.
Yeah. But it could be, it's limited by your how much surface piping, because your surface distribution infrastructure is, as you'll see, makes up about 45% of the total capital cost. So you could make it as large as you wanted, it's just pumping hot water around, but your efficiency comes in trying to make it as small a footprint as possible.
Right, but would it, say, service a subdivision or bigger, smaller?
Well, I think it would look great around downtown Toronto. It depends on local conditions, but I'd say around here you could say maybe 50 acres, a 50-acre subdivision, something like that. And
still get that relative coefficient of efficiency there?
Well, you're going to have a little more pumping involved. Again, that's distance related, and but the main pumping is pumping the water up and pushing it back down again. Okay. That's probably 80% of your electrical load.
But you get some transmission losses in pumping it still.
Of course, yeah.
What about, you could essentially use that system anywhere, it just depends how deep you want to drill to find that layer, right?
Well, that layer is fixed where it is right now, so at Moose Jaw, the conditions are, 68 degrees or something like that.
I'm asking for anywhere in the country, though.
Well, it's not in Alberta.
No?
Yeah,
crap.
It depends on the local geology. It may well be sitting under your back door, just nobody's talking about it. Yes?
How much of that 5.8 million that you've estimated is design costs, and is it feasible for a system to be designed for, say, Moose Jaw, but easily replicated in Regina, Estevan, Weyburn kind of thing, and maybe perhaps a couple communities get together to design the system? Is that feasible? There
would be very little additional design cost, because to get it to what we see on the picture here, this is all pretty well known. A very minimal amount of engineering would have to go into going beyond this. With those costs, the costs I've include the 2 wells, plus the engineering and developing that load center. So most of those costs are included in this. But again, what's not considered is the distribution system.
But approximately in that 5.8 million, how much of that is design? Just a rough.
Probably not very much of it.
Not very much.
No, not very much of it. Again, these oil field things, they're almost boilerplate. And this is just a heat exchanger, or this is just a heat exchanger. So it's pretty standard stuff. It's a titanium heat exchanger, but I'd have to say the additional design would be in the actual distribution system. That most of that design would represent a fairly small amount of this total capital. Yes.
What's the difference between the geothermal that they had in Northern California that ran dry compared to this geothermal?
Well, I believe what you're talking about is that was actually very high temperature. That was steam that they were generating, or hot water that would flash on surface, and that was used for power generation. That would go right into a turbine and be used directly for power. What happens sometimes is these can deplete. And if they didn't actually drill a hole somewhere nearby in the appropriate location and started to inject water back down there, then the natural pressure there just kind of relaxes. And so so production would decline. I think that's what happened there. So you have to actually complete the other side of the cycle. Some of those systems are great to begin with, but they decline because they're losing energy as they let their steam out, their water out. Yes?
Brian, the water is under pressure when it comes up. So do you have to reduce the pressure to run it through the heat exchangers? No,
it actually wouldn't be under pressure. It would be, if you just drilled one of these wells, the natural head, or the natural pressure in the aquifer would actually push the water up to almost near the surface. At Regina, it's only about 12 meters from surface. That's where it naturally wants to rest. It's almost artesian. It would almost flow. But to pump the amount of water we're talking about, the 660 gallons, we'd have to place a pump about 300 or 400 meters deep into the hole and pump the water, and that would actually draw down that natural water level. And I think it would be similar at Moose Jaw.
Well, I know from the spa that the water was under tremendous pressure.
Yeah, different geology.
Oh, okay.
We're talking about altogether different rocks.
Different rocks? Okay.
Yeah. One of the issues with the spa was when there was so much pressure, it was artesian, there was so much pressure available there that when they were to capture the heat out of it and then try to put it back, they had to fight all that artesian pressure. So it actually, the energy penalty to put it back there was really significant. Whereas for the dead wood, it still has to be pumped back, but at a lot less energy penalty. Yes. Sorry.
What happens when you get to this year 60? What happens in year 61?
Well, there would be a slow decline. It would just start to drop off slowly, and then at some economic cutoff, wherever the minimum temperature was, maybe it would last for another 3 or 4 years, depending on what the utility was, or 5 years, or what have you.
The second part of that is, isn't there sort of a whole bubble then of reduced temperature building up towards the surface?
No, it's all just within this aquifer. All the heat is extracted from this aquifer. There'll be some heat extracted from the rocks nearby, 10, 15 meters either side of the aquifer, but for the most part it would just be the water in the aquifer.
So that whole surrounding, I guess what I'm asking, that whole surrounding area, like for a kilometer on both sides of that, is no longer available? Well,
the area between the wells would be cooled. So at that point, depending on the conditions at that point, another well could perhaps be drilled over here. So you maybe have 3 of them kind of thing. So it's not truly a renewable resource. It is in the long term. The water, again, is moving very slowly in here. We think less than 2 meters per year. So that's really not contributing much more new hot water. But you know, you take that out, and if this became declined in value, in thermal value, and another well was drilled here to develop another loop, this might take about 100 years or more to reheat. So it's not renewable in the sense that, okay, now I can go, you plug into it again. It would take some time. But we don't really kind of promote this as being renewable energy, although in the long run it is. In geological time it is. Yes?
My question is kind of related to the other gentleman's question. If the life expectancy of the well or the system is dependent on the distance where you're entering the aquifer, what's limiting your distance? Can you expand it to 2,000 meters?
Well, this model is based on 1,000-meter separation from what the university did back in 1980. So we just stuck with that. But what really limits it is drilling risk. In this district here, if we were to actually build one here, kind of the ideal drilling parameters would be take it out to 12 or 1,300 meters. And how that's determined is as we start to, it's one thing to drill vertically, it increases the drilling risk once we start to drill directionally and deviate from center. And that risk increases the more we reach out. It's like reaching off the edge of a table, it just gets riskier for drilling reasons. You know, you could get stuck in the hole or have additional hole problems. But 12, 1,300 meters, those aren't really significant issues. Beyond maybe 1,300 meter separation, you have to consider additional drilling risk.
And my other question is that 60-year lifespan, that's really an estimate because truly pretty tough to predict that? Or,
Well, that's based on modeling, theoretical modeling that was done back then, which we're going to try and review that here over the next couple of months to see with better modeling abilities that we can do now. We're going to try and redo that. But that was based on reasonably reliable modeling at the time. Of course, that was assuming that the character of that aquifer was homogeneous, and we know it's not. But we kind of do the best we can with some of these forecasts. Yes?
Yeah, I was just wondering, would earthquakes have an effect on this? Like we had one just recently in Esterhazy, wherever that is.
Well, that was induced from potash mining.
But then I also come to fracking, like if there's gas or oil exploration, they're blowing up rock underground. And,
well, to address the first part about earthquakes, this aquifer has been here for 500 million years now, It seems pretty reliable and continuous, so I don't think it would change too much. It might alter things a little bit, but it's I don't think it would make too much of a difference. Not the kind of earthquakes we get here. Like we might get a 2 or 3 magnitude earthquake here, which is not very much as an earthquake. I think the risk would be really slow. Sorry, what was the second part you asked about? About hydrocarbons?
The risk would be more to the collapsing the well.
Well, no, we're not actually taking anything out of it that isn't going back in, so we're not creating a void.
No, but you could break the pipe or whatever.
Oh, from an earthquake?
Yes.
Well, only if it faulted right through the pipe. So, you know, that could happen. Pretty unlikely, but it could happen. Yeah. With respect to hydrocarbons, most of the hydrocarbons in southeast Saskatchewan are higher. Most of like the Weyburn field, for example, it's at about 1,600 meters, which would be the equivalent to about 1,000 meters at Regina or Moose Jaw. And our potash operations are in the same rough zone, so they're quite a bit higher. So there wouldn't really be any interference. I mean, we drill through most oil wells, when they drill beneath the salt-bearing zone, just drill through it with no particular problems into a lower hydrocarbon-bearing zone. So it's not, again, these are all just standard oil field practices that we can deal with. Yes?
What are the effects of cooling going to have on the salt? Is there any danger of solidifying it? And the second question I have is, can you put the heat exchanger in the aquifer?
Well, in a way, we have a heat exchanger in the aquifer when we put the cold water back in.
Oh, I know.
But no, I shouldn't be glib. I'm sorry. I don't to put the heat exchanger in the aquifer.
That's one question. Yeah.
Yeah, I'm not sure how you get it down there. We're 2 kilometers deep, and we've got an 8-inch hole kind of thing. So, I mean, there has been talk about using a single well, and there are some technologies that can do an exchange, but it's such a long distance. Like the 2,000 meters is such a long distance. Even if everything's insulated, the potential heat loss through that insulation as it travels 2 kilometers is so potential, especially on such a small wellbore. But I think there has been some investigations into that. And the salting issue, the water around Moose Jaw here would be about maybe 100 grams per liter total dissolved solid. And if it's nowhere near saturated, so when it came to surface and had that pressure drop, there's a potential when we drop the pressure of a water with salt in it that the salt will precipitate out. But we're not going to drop the pressure. We are going to drop the pressure to atmospheric temperature or pressure almost. But the salt in the water is nowhere near saturation point, so we don't expect any precipitation. Now, if there is some precipitation, again, this is not an uncommon problem in oil field production, that there are ways that you can try to address this by trying to keep the pressure higher on surface, that kind of thing, so you won't have a salt dropout. Yes?
One of the earlier diagrams that you had where you're showing where you basically got your plant, heat exchange plant, you see the red and the blue going down, and that's fine. But I only seen the red arrows feeding out. You definitely have to have circulation. It's got to go up and come back, right?
Yeah, that wasn't a very good picture.
Oh, okay.
There should have been 2 lines.
Okay.
There should have been a blue line and a red line, but I didn't think anybody would pick up on that.
Sorry.
That's why I've already asked Philip if I could maybe borrow a slide so I could show that in the ground. It'd look a lot more realistic.
Okay, but I guess the only the second part of my question is just, I know where there's heat, it'd be nice to cool. So is there any other potential strategies to provide cooling in the summer?
Not with this source. It's not hot enough to provide any cooling through heat pumps and such. So no, I don't think so.
But I mean, even just the way that the design of the pipes, if there could be even maybe some other form of cooling lines that could be included just laterally somewhere. You could turn it on in the summer and turn it off in the winter, kind of exchange it in a different way, still utilizing the entire heat plant and everything else.
Oh, of course, and really if we look at the example in Toronto, that's what they did. They put their cooling and heating lines down together as all part of the same district heating project. Yes?
It's not really a question, but as you mentioned, Toronto, we also have a couple of projects using ground source heat pump, much shallow, well-designed, which work, but I think the key is in the situation you described. As long as we identify the load and the heat exchange plant, that's a very major decision already. So even the source may deplete over a number of years, we can always use other alternate energy source. Because the most expensive, I wouldn't say most, but a significant of investment is on the upper ground, the thermal grid. Once you establish a thermal grid, the rest are easy. So, I think it is really important at the initial stage, as you mentioned, work out all the technical details. But a sound business plan is the key to success.
Mm-hmm. Mm-hmm. Any other questions?
Yeah, right here.
Yes.
Any advantages of drilling where there's springs?
Well, if it's warm enough, we want to get to the hottest water we can, of course. And the other, and again, this is standard oil field practice, is we want to isolate and not interfere with any kind of near-surface potential groundwater. The water in the deadwood it's very briny. It's not of any potential use for any kind of domestic consumption. But of course, near-surface aquifers are. That's one of our main sources of fresh water. So we'd go the opposite way. We would very much try to isolate any kind of contamination or interaction with surface waters.
You see, in the hills just south of Moose Jaw here, some 25, 30 miles south, there's lots of springs that are used on farmland or leased land, whatever the case is. And they've been providing a water supply for years, of course.
Mm-hmm.
But no advantage whatsoever.
I don't think so. They just wouldn't be. We're looking for heat.
Yeah.
We want to mine the heat out of the water. So. Well, maybe I'll just move on. If you think of other questions about this system, I'd be happy to come back as well. So South Central Enterprise Region engaged us to do a very high-level preliminary concept, and I mean very high level. We made a number of really big assumptions, but we tried to get our minds around a residential subdivision at Moose Jaw to see how that might look. So we assumed it would be 70 acres in size, and a mix of single-family and apartment units. And of course, there would be a district heating system accompanying that. We didn't even consider cooling at the time, but that would make perfect sense to include as well. And again, just to remind you of this imperfect system, all these lines would be doubled, of course. We're really looking at the like an or a residential, perhaps maybe light commercial or something like that. So each house would need to comply with certain building methods to actually work with this. We're dealing with a warm energy source, not a hot energy. Like your furnace is a pretty hot source point, but we're talking about relatively cooler water as a heating source. So each house would have to have an in-slab radiant heating in their basement floor and have a heating coil in their furnace ductwork, as well as a high-efficiency furnace. The furnace would supply supplemental heat and air conditioning. The heating coil in the furnace ductwork, if you can imagine a coil in the upper part of the plenum of your furnace, the geothermally heater water would be circulated through that coil, and it would still be transported to your house by the furnace as well. So it'd still be forced air to actually move this heat around. And on this again, it would be designed for base load, so this would provide all the heating necessary to say -15. And on days colder than that, the furnace would supplement as well. So you'd have the furnace would cut in at that point. Apartments would have in-slab heating as well, and of course a backup boiler for supplemental heat. These systems could go down. The geothermal system could fail, so there has to be backup heating as well available on every unit. And of course, each unit would have a separate natural gas meter and a geothermal BTU or gigajoule meter for invoicing purposes. So we had a bit of a conversation with the city about what kind of density we were looking at for 70 acres, and they wanted to look at 7.5 units per acre. So we came up with just made this up really, 300 single family units and 225 apartment units totaling 525 residential living units. The geothermal plant is about $5.8 million, and that again, that includes everything in that other slide with the 2 wells and essentially the heat exchanger plant, really something that could be hooked up to provide the distribution. And you'll see again, the district heating infrastructure is almost 45% of the total cost. So you can imagine already how density impacts this. The denser the user is, the less that cost is going to be, and it's going to make this more affordable. So we're looking at a total cost of about $11 million. The per unit cost of $20,300, that represents how much each average household, if the householder was paying for this, it would cost them about another $20,000 if they were part of the utility that was providing this energy. Or that's the cost for the utility. That's the cost the utility, whoever built this thing, would bear. But each individual house or living unit has to have the in-slab heating and the exchangers and controls, and it would cost an additional $10,000 roughly for each house to essentially tie in to the geothermal source. But so the total cost per unit is about $30,000 to have this. But again, the economics of this is based on the avoided cost of natural gas. And we've made many assumptions, as I've said, when we've come up with a payback on this system of 36 years. For really out of interest's sake, to see, well, how much value would including a CO2 emission avoided credit add to it? And you can see that impacts this significantly, reduces it down to 22 years. Again, I'm not suggesting that could happen, this is just in the conversation. Now, 36 years is a long time. We were very conservative on this estimate. We were actually only utilizing about 60% of that heat available. We wanted to really cushion this because we kind of had one crack at a model, so we cushioned that. As well, it really speaks to when you consider where it might lead us, I guess, is when you consider that additional cost for the distribution infrastructure, it really pushes us towards very high density housing, maybe a commercial or industrial space to anchor a project like a hospital or something like that, because their utility is very high. It's a lot higher than a house because their domestic water load is so high. So maybe anchor a project with a larger complex like that, and it would significantly hopefully reduce the amount of district energy infrastructure that's required. So if Moose Jaw, for example, were to develop an eco-energy neighborhood incorporating as many things as possible, the many we've heard of already, and a geothermal heat source, there's a lot of high-value intangibles associated with that. Moose Jaw is already a pioneer in Canada for developing geothermal energy, and developing a neighborhood of some kind would be the first of this kind of thing in Canada. Again, geothermal is a new source of energy. It's a brand new source of energy that we're sitting on and not utilizing, and it has a very small environmental footprint. By developing something here, it provides, it would add to our provincial supply mix and develop expertise and technological development right here. And of course, there would be increased capital value in homes because they have intentionally reduced their carbon emissions. So that's what we found for our investigation, and be happy to take, I think that's my last slide. Oh, pardon me. Getting ahead of myself. I guess something I foresee is geothermal, when you compare the price of natural gas, I mean, it's exceptionally low right now, but I think it's foolhardy to think it's going to be low for a long time. It's our most wonderful burning, clean burning fuel that we have. And I would be more comfortable forecasting the price of gas based on the last 10 years, not the next 10 speculative years, because there are no accurate gas forecasters around. So to say it's always going to be low is I think, foolhardy. We need to plan longer term than the market of natural gas. By having a demonstration project, we have the opportunity of learning how this works in Canada. And because it's, I'm convinced that at some point there'll be a major tipping point with the cost of hydrocarbon fuel. And we'd be best be in a position to know how this stuff works before that actually happens. One of these systems could provide all the heating necessary in Pence, for example. There are hundreds of communities in southern Saskatchewan that could own and operate their own system and be completely, not completely, but significantly self-sufficient in their most basic heating needs. So as a demonstration project, this needs to happen somewhere so we can prepare ourselves for when this will be very feasible to do. So is there any other questions? Yes?
You had mentioned that it helps to have something like a hospital or something big to anchor something because of its high domestic hot water use. So it would be used for domestic hot water as well?
Sure, through an exchanger, sure.
So if you're doing that, is there a reason you couldn't have just a hot water heater and a fan cooling these homes and forego the furnace altogether?
Well, you need backup.
Right.
And for supplemental heat.
Right, but you could have your hot water heater as your backup. I'm saying you could you could combine those systems and get some of that payback down.
Well, I mean, sure, I never thought of that before. That's kind of the opportunity here, is to combine as many ideas as we have. I mean, there is no silver bullet anymore. We can't just burn gas, period, or burn coal.
Right.
But geothermal isn't the only solution. It's building standards, it's combined heat and power. It's all these things together. We have to think about fitting all these together. Yes?
Actually, I was just thinking pretty much what Trevor was. We didn't have a conversation on this one, but for instance, instead of the cost it takes for, I mean, sure, a high efficiency forced air furnace and then putting a coil system in it, I mean, already as it would be, you're also using high hydronic inflow heat and so on. So even instead of just the actual hot water tank, you can have a gas hot water on demand system as your backup for your both hot water and also for the supplementary heat that you needed in the system, because it's all piped in. Regardless how you're doing, when we talked about the design of a home and the energy efficiency and so on, you're going to have an HRV. You design your HRV that is not going to be going any plenum because you don't need it in plenum. And then in this case here, the HRV could still do some fresh air and have air distribution throughout the house, because that's the problem with these systems. Everybody says, well, we want circulation. Well, the HRV is your circulator. And then that is a very simple system, so you don't need all the square footage to have a furnace. Mind you, they're making much smaller nowadays. So I mean, there's all kinds of potential, but just using just a gas-fired on-demand system, probably.
Of course, of course. But if all the houses are built like these, we'll probably do thousands of houses. Yes?
Is there any estimation, like when you talk about supplemental heat, and even a hot or instantaneous hot water heater or something like that? I think I know the answer to this, but is there any estimate as to how much it would be used compared to the geothermal system? Like, I guess what I'm getting at is, can we tell people who are buying it, it's going to take 90% off your gas bill, but you'll still need to pay a little bit of gas?
We didn't try to determine that, but it would lead something towards that, yeah. Yeah.
For extra sweaters.
Yes.
Just a suggestion that one thing you don't do is mix radiation and forced air heating, because you're going to reduce the efficiency of the radiation. Radiation is a low temperature system, and it will run any demand, and it's at about not over 40 C. If you mix them, radiation inverse stratifies, and it takes 30% less energy, minimum 30%. I think in our climate it's probably 40% than forced air heating does. Mm-hmm. So if you're going to use a supplementary system, put it into the radiation, into the floor system, not the forced air.
Sure, that might make sense, yeah. Yes.
Counterpoint to that, because I build houses with both all the time. And what you have to do is, you're right, you do have to use a lower temperature for the radiant system, so you mix that down with something cooler. But to do radiant heating only is very expensive because of the infrastructure that you'd have to put in to the places where you put it. You need concrete, you need something thermal. All that stuff costs more money. It's relatively inexpensive to do it in your basement because you got the cement there already. And then on your main floor you use forced air. You have to have that distribution system there anyways.
You don't need forced air.
Well, we kind of assumed that people in Saskatchewan would want air conditioning too, just by nature.
You can cool with the floor as well.
Yeah.
That's done all the time in Europe.
Yes, you can, but you still need that cement. They build on slab on grading here, but they don't do in basements, right? So.
But you can put slab on the main floors too.
Sure, but it's another $5 or $6 grand.
Well, that's kind of a lot of offset costs there.
There's a lot of things to consider. I think we can agree on that.
Well, we've done 4,000 radiatory heating systems in North America, so I barely know what's going on.
Sure.
I think this is a really good example, though, of you taking engineering and thank you, Brian. I think you've got the underground stuff captured, but this is where joint venture comes in.
Yeah.
You take the expertise, especially all of the things that were learned in the building sector. Vic, I know the work that you've done and the brilliance you bring to the job, and some of the work you've done in Alberta, learning from experiments. I think it's a great opportunity to try to figure out what is the magic there, and nobody's done it before, and maybe in Moose Jaw. You know.
Why not Moose Jaw?
Why not Moose
I
Jaw?
think it's a great system.
So.
Yes?
The Toronto project that we got presented was obviously redevelopment of the core area and replacing infrastructure with new, more energy efficient. So this kind of feasibility projection you've got assumes a 70-acre subdivision starting from scratch.
Yeah, a new build.
Has there been any sort of parallel consideration to redevelopment of core area, like a downtown development strategy where those commercial and institutional partners are already there and replacing themselves as part of that? I mean, that's an issue we're obviously faced with as well.
Of course, of course. I guess it depends. If they're tearing up streets, that kind of thing, if they're doing a major reconstruction and streets are being torn up, as you know, it costs a lot of money to open a street up and put a water line in and close the street. I mean, if that's going to happen anyway, then your district system may make more sense.
Believe me, we're doing it every day.
Yeah.
No, we shouldn't be doing it.
That's right.
When they can afford to.
Yeah.
But I mean, it's a different equation, but it's equally weighty in terms of the possibilities.
Yes, and it depends on what the existing building is using it as an energy supply. If they're a steam system, for example, to incorporate a hot water system with it would probably make lots of redundancy. And that would add a lot to the capital cost, so it might not be a very good fit. But then you can use heat pumps for upgrading, perhaps. So lots of, I wouldn't say no, but there's lots to explore there. Yes?
Just to sort of add to what your comments were, and I can kind of see where you're trying to put the puzzle together and say, well, look, this is all great, we're all in the room. I'm not too sure the community or the city has actually done this yet, and probably so. This is almost like a visioning exercise almost, where we're really putting all these ideas together. But the other thing is actually, as I mentioned earlier, up in the north of actually having a charrette. Well, in designs and concepts like this, it's probably not a bad idea to look at an actual community design charrette, where you're bringing in all the experts, engineers, designers, all the kind of stuff, the builders, the developers, the city, and everybody that has everything to do with it, and community members, to all pool themselves together to actually put everything on the drawing board. Instead of just one person here thinking, oh, that's a great idea, that's what I'm saying, and when it's really connecting.
So if I could get you a room at the spa again, would you come back and help us do that?
Possibly.
Okay.
If I get the really high-end room. No, I'm just kidding. I got the room that's right above the door, it keeps slamming on me. I got the sheet room.
Just make sure you put somebody in charge, because if any of those shreds, and if you don't have somebody in charge, you're just going to have a whole bunch of people like me and him disagreeing on a bunch of stuff.
Yeah, it has to be properly run, and you need a good facilitator for something like that. But the thing is, it's a real great way to get all of the movers and the shakers and everybody all together in one room to at least try to hash it all out. It's not always rocket science. It's not always promising that's going to give you all the answers, but at least it's your best bet to be able to pull everybody together to come to certain commonalities and common decisions and try to at least move in a certain direction. And you know what? It could work and it could totally turn the opposite direction, but the fact is that you got to throw it on the table and hash it out, find out where the numbers work and so on. Like I'm almost thinking even an example for all the lines, and we're talking about busting up streets and so on. I was able to have a presenter in once at one of these other workshops I had done that talked about biomass and feeding to communities. And they're actually pushing their lines underground, so there's not a lot of disruption to whatever existing infrastructure there is. So, there's, it's just ideas. You got to get them all together, figure out how these things could work.
This particular model was based on a new subdivision where you don't have the cost of ripping things out, because you can see it's challenging as it is, whether you can apply it or not. I know we looked at it for the multiplex and whether we could tie in. The big cost was ripping up the street, not putting in the new line and tying in. So yeah, the reality of cost really comes through if you're doing rentals.
Well, thanks, everybody. I'm around if you have any questions.
Thanks, Brian, very much for that presentation, and thanks to South Central Enterprise Region for facilitating that as well. Just a couple things here before we're done for the afternoon. The next sessions will start at 4 o'clock. They're concurrent sessions. So in Sarah's dining room, which is just outside these folding doors, we're doing the Green Educational Opportunities. Angie Bugg from the Saskatchewan Environmental Society will be conducting building operator training and energy awareness training as well. Some overviews on that and what they offer from the Saskatchewan Environmental Society. In here we'll be undertaking a session called Seizing Opportunity in Building Communities. We had a cancellation. Alan Thomarat is unable to attend, but we do have Derek Thompson from Dharma Design, who is in charge of the West Park subdivision, one of Moose Jaw's newest subdivisions, will be filling in for Alan. And as well, we have representatives from the Housing Advisory Committee of the City of Moose Jaw. They'll be conducting that session together. So Derek and the Housing Committee in here, and Angie in Sarah's dining room. And those will be starting at 4 o'clock. And don't forget tonight at 7:30 to come by in this room as well for the evening presentation. And that's about it. Were there any questions on anything? All right, still coffee and muffins, and we'll reconvene at 4 o'clock at those two locations. Thanks very much.
Geez, I haven't sat this long since I've worked for a living.